forgot the uploading the last class to YouTube. So maybe today if I find the USB, actually I lost it. But if I find it, maybe that is in my home. So I will upload it. Maybe previous one is it it disappeared. It is disappeared, and I used the new USB 2 weeks ago, and actually I lost it too. But maybe it is in my home, so I'm believing. No, I organized my room, and so it is not messy. But I just all item put on my like nearby closet and my table, and so maybe there is in near there. Yeah. Today we will talk about dimension of a vector space. It's a little slow. I need to write more larger. So the dimension, we already saw what is dimension in previous chapter, like n-dimensional real space is actually n, and by constructing standard basis, we saw that n-dimensional space has n vectors, like n vectors is basis. And tuple is also it is will be written as an n tuple of maybe. A1, A2, AN. In this vector space, we'll denote the elements as an n tuple, but it is the vector space of polynomials with less than or equal to the degree d. And in here, we will bring the vectors from A0 plus A1x, A2x square, AD, XD, like this form. So in this sense, we want to say it has n plus 1 dimensional, because it is similar to just n plus 1 tuple A0 to AD D. So then how we can define the number of dimension, if you ask, this answer will be, the dimension will be give the answer. So we only saw a standard basis, but when whatever you choose any basis, you will get same number. Then I mean we need to prove that the following main 0. All bases for finite dimensional vector space have the same number of vectors. And as a spoiler, it will be the number of basis vector basis. And to prove it, we will need the more mathematical theorem, because if you define like this, then it is hard to prove what we should prove. So we will divide it to two theorem. One is when we define V is be a finite vector space, because we said we will discuss in finite dimensional. So V is finite dimensional. Vector space, and let V1 to Vn be any basis for V. Finally, we will show that first, if a set V if a set in V has more than n vector, because we have n vectors, so has more than n vectors, then it is linearly dependent. This implies if you bring n more vectors, it will not be a basis for V, because the definition of basis was linearly spanning set and linearly independent set. So the linearly dependent mean it is not a basis for V. And the second one is then we will talk about the spanning set. So if a set in V has less than, fewer than, n vectors, then it does not span V. It implies if you bring fewer elements, fewer vectors, then it cannot be the basis for V. So to be a basis for V, we need exactly n vectors. So if you believe this theorem, then we can define what is basis. That is the number of bases, because it will not be changed by the above theorem. We will prove it later. So the dimension of a finite dimensional vector space V is denoted by dimension of V and which is divided to be the number of vectors in a basis. For V, because if this theorem is true, then as I just said, the number of bases will be exactly n vectors, so it is well defined. If we see example as we see before, the dimension of r to the n will be n, and the dimension of p to the n will be n plus 1, because the number of standard bases is n and n plus 1, and the matrix n by n matrix case will m times n. It comes from the standard basis. It is enough to show the number of vectors in the standard basis, because the number of bases will have same number of vectors. And also we can see that when S be a linearly independent set, we want to be a linearly independent, then span S has dimension R, because spanning set is a vector space, and it will have S as a basis for this vector space. And the vector space, since S be a basis for the spanning set, so the dimension is the number of elements in S. Let's see one exercise. We already saw that the homogeneous system will give a vector space as the solution set. So we might be able to find the basis for the vector space and the dimension of the solution space of the linear system. Six x2 minus 5 x3 x2 x4 plus 4 x5 3 x6 is homogeneous equation, so the right side is all 0. 10x4, 15, x6, and 2x1, 6x2, 8x4, 4x5, 18. I will change this part. I think it is typo. 3x6 and 18x6 equals 0. Then if you see this homogeneous system by editing the second row and third row, you will get the last row. So it is linearly dependent, and if you find the Gaussian elimination, you will get, maybe you will get these pivot elements and free term. So there are 3 free terms. That means it has 3 free elements like T1, T2, T3 in a basis field F. Let me write it in real number. So it will give the dimension of this space will be 3. And actually, it also can be written, can be found from the number of variables. We have 1, 2, 3, 4, 5, 6 variables. So the variable number is 6, and we have linearly independent 3 equations. The last one was linearly dependent from others. So the number of linearly independent polynomial is 3, and by calculating the number, by subtracting these 2 numbers, we can get the dimension of this homogeneous equation. Because one equation will reduce one dimension by, because if you get an equation that will give one variable from another's, so that means it will reduce the number of variables, the number of dimension. So, I mean, in homogeneous case, you can get the dimension by calculating the number of variables. In this sense, as we have seen, not only for this equation system, but we also can see n+1 dependent set will be reduced just n dependent or not or independent set. So to prove these 2 main theorems, we will focus on the editing or removing, inserting or removing elements to a spanning set or independent set. So let S be a non-empty set. finite vector space V. Let me read. V is finite dimensional vector space. The first one is if the set S is a linearly independent set, and if V vector space V that is outside of spanning set of S, spanning by S, that means V is not in span S, but V is in V. Then if you construct a set, a finite set S union V, is still linearly independent. It's a little simple because since you have already linearly independent set, and then any vectors in S will not will have independence, and the vector V cannot be written cannot be expressed by any composition of S because of this property. So V is also linearly independent to the set S. So the union set will be linearly independent. And the next, we will talk in the sense of spanning set. If V is a vector in S that expressible as a linear combination of other vectors. It is the converse condition of A in S, and if I will skip this notation part. If we set the subtracted set as subtracting V, it is just real set minus same to the spanning set of V of S, because spanning set was just a linear combination, and if we don't have the vector V, which is expressed by linear combination of other vectors in S, then the spanning set also has V in here. That means the this set S minus V will express all vectors in S, and it is that means it has this inclusion property. And if you bring all S minus V is the subset of a subset in S, so it also satisfies it the converse way. It is a subset, and V can be expressed as a linear combination. In combination of vectors in S. So the spanning set is same. By using these facts, we can prove the main theorem, our main theorem. But before we see it, I will give some examples. It's exercise, but I will not give it as an exercise. We will solve it in this class. Verify that the linearly dependent set S 1 minus x squared 2 minus x squared x cubed x squared plus x cubed give. You can check this is linearly dependent by giving coefficient and C1, C2, C3, C4 equal 0, and there, if you find not all 0 coefficients, then it will be linearly dependent. But if its solution has only all 0 CIs, then it means linearly independent. But you can find another C1 to C4 in this equation, so it is linearly dependent. The fact that so from the previous theorem, you can find the vector V in this case. Let me use the last one, x squared plus x cubed. It is same because this element x cubed plus x3 can be written 2 minus x squared minus 2 or minus x squared. It will be x squared plus x cubed. Then by linear combination, by constructing a linear combination of this, we can express x squared plus x3. We can see the spanning set of 2 minus x squared, x minus squared, x cubed already has x squared plus x cubed. That means if you editing the vector x cubed plus x squared plus x cubed is also same. So the n-dimensional from this reason and from the differential basis, we defined it we defined the dimension of a vector space is the number of vectors of basis. So that means if you consider consider the n-dimensional vector space, and as we have said, with n vectors, then the we can see a criterion is S will be a basis or not by seeing two fact. One is S span V, and other is S is linearly independent set. Because all bases will have exactly n vectors if the dimension of V is n. And then from the definition of basis, to check is it basis or not, we will check the spanning property and linear independent property. If you see some example, set V1, V2. Emergency. You can check what emergency alerts. Okay. Then it is a basis for R to the 2. It is by using this theorem, and from the definition of basis, you can check C1 V1 plus C2 V2 equal 0. Then by the from the first element, you can see the equation 5 V1 plus 3 V2 is 0. And from the second equation, you can get V1 minus 7 V2 equals also 0. So it will give not V1, C1, C2. C1 and C2 are all 0. So it is linearly independent. And if you see the number of dimension, the number of vectors, you have two linearly independent vectors. Then the spanning set dimension will be 2. And we already know the dimension of actually 2 is 2. It is same. That means from this theorem, if n vectors has n dimensional vectors has same number of vectors, then if the vectors v1 and v2 in the vector space are actually 2, it will span R to the 2. Yep. Yeah, the rank system of vector, the rank system of matrix will be analogized from the operation, and it is maybe you learned already what is rank. It is the image of operation or linear transformation, and since from this basis theorem, this dimension theorem, it will satisfy the equation, the dimension of V. Here V is a vector space and T is a linear transformation from the vector space V to W. Then this is same to the rank of T and nullity of T. We will see this from the next class. We are seeing just a set in solution set from homogeneous equation, and then the homogeneous equation we have previously we saw 6 variables example. That means the dimension of V is 6, and we saw the number of equation and what is the dimension of solution set. So we divided the two things, and so it is very important theorem, and we already seen that fact as a simple example. Okay, then now that is not same. And if it that is not same. But if you see some removing the nullity parts, then it will be same. That is also right. It is more larger than rank. Okay, then now let me see that. Let us be a finite set. Of in V. Then first one is about linearly independent. If S spans V but is not a basis for V. That means to be a basis, we need linearly spanning property and linear independence property, but this means it does not have linearly independent property. Then S can be reduced to a basis for V by removing appropriate vectors. I will explain it simple. If S is a set of vectors that spans V but is not a basis V, that means it does not have linearly independent property. Then some vectors will be linearly dependent. Then by removing the dependent vectors, and we will check the linearly independency again, and by removing that vectors, we will get linearly independent set. And from the definition of basis, it already spanning the vector space and it has linearly independent set, then it will be a basis for V. Similarly, if S is linearly independent set, but it's not already span it is not already a basis for V. That means it's not a span. It is not. It doesn't span S. Span V. In this case, then this S can be enlarged to a basis for V by inserting proper appropriate vectors into S. It is also almost in similar property with this theorem. If it is linearly independent but is not a linear basis, this means it does not span S. So it does not span V. It will be a subspace in V. Then by adding the elements V minus span S V1, the spanning set V1 S union V1 will be an independent set because of the previous theorem. It will give them one more larger dimensional vector space, and repeating this process again and again, then we will get the vector space V when it has n vectors. The proof is very simple. It is all just checking the previous theorem. So I will skip it. So in finite dimensional vector space, the dimension will give convenient property for stable vector space. We want to consider like this equality, then we should consider finite dimensional vector space's sub-vector space will be finite or not, and we will prove it. Because homogeneous equation will give sub-vector space of the domain space. And in this sense, the subspace, if not a finite vector space, then we cannot calculate the dimension. But it will not happen from this theorem. Return. W is a space, subspace of V. Then W is also finite dimensional. And the dimension of W is always less than or equal to the dimension of V. Also, the meaning of the vector space W is equal to V is that the dimension of W is same to the dimension of V. I think if you prove the first theorem, the property A is finite dimensional, by proving this, you will get the another one as well. So I will focus on the proof of A. I will set a spanning set. I will use the previous property. So by constructing a spanning set of V, I mean like S prime span W. Then by since W is a subspace of V, by inserting vectors V in W minus V minus W into S prime, that means we will make S prime union V. It will be linearly independent set because not linear independence. It will span for larger vector space than W, because V is not in W. So W. Oh. It is S prime, and subspace. It is subspace of S prime union V1, and by giving this is W1, by denoting this is W1, then we can repeat this process again, like bring V2 from V minus W1. Then it is not in W1, then it is not in W, and by making this V1 and V2 will have a linear independence property, because we bring V2 outside of V1. By repeating this, we will get a space, get a set S it has S prime, and that spans V. I mean, spanning of S is V. If you bring this at least inserted set S from this inclusion, we will get a basis by using the second by using the first property. I mean, by reducing the vectors not independent, we will make basis for V. It is always possible to bring basis from S, because S is spanning V, and as I just said, the first theorem is saying by removing linearly dependent vectors from the set S, we will reduce to a basis for V. And we want to get the basis for W, because we want to get the dimension of W. Then from B, we might be able to get B prime. B prime has V1 to Vi's vectors, which are not in vector space W. From the process how we choose it, we choose V1. We choose V1 is not in W, and V2 is not in W as well, because it has W. So VI's are not in W, then by restricting W, the vector V1 to VR will be removed. Then the space still span W because we do not remove any vectors in W, then the spanning set of B prime will be W because spanning B is V. So by bringing this set B1, it has a linear independent property because of this B is basis for V, and it span W. That means B prime is a basis for W. From the definition of basis, then the number of elements, the cardinality of B will be larger than or equal to B prime because we just use restriction, only restriction. So the number of elements in B prime is less than or equal to the number of B. Finally, we already know V is a finite dimensional. Then finite dimensional vector space, the less than finite dimensional vector space's dimension is finite dimension. So it will be proved W is finite dimensional. And from this, we already see the fact that because of B prime's cardinality means dimension of W, and the cardinality of B means the dimension of V. So it has this inequality. And also, if the dimension is same, means we do not any vectors can will not be wouldn't be restricted. That means the set of W is same to set of V. So if the number of dimension is same, then W and V is same. Conversely, if the vector space W and V is same, it is obvious that the dimension of W and dimension of V is same because the vector space is same. Now then, we saw that what is dimension and